All right, so let's recap what we did on Monday. We went through these transfer functions, and then the one thing that's left to discover was this compensated error amplifier transfer function, right? And we learned that having this block is actually important, right? It's actually critical. It's a must. It's required. Right? It's not an option anymore, right? Even though this is not part of the original system, but it turns out to be that we need this, right? The reason being, if you keep the remaining transfer function without the compensator, then we're not going to get the open loop stability requirements or criteria for DC to DC converters. So, namely, high gain at low frequencies, low gain at high frequencies, right? So just with the three blocks right there, right? The PWM, switch, and filter and load, you will get something like this, right? Without ESR, you can see that the high gain is met, which is low gain, right? But the low frequency, the high frequency, I should say, the high frequencies requirement is met. As you can see, it's low gain, but the low frequency requirement is not, right? You can see the gain is also low, supposed to be high. Same deal with if you include ESR, right? So we must add something to this transfer function, and that would be the use of this compensator, right? So type 2 amplifier, what we covered last time, and it looks, the shape of the gain plot of the compensator looks like this, right? Which high gain at low frequencies, and then a flat gain in the middle, mid frequencies, and then and then also low gain at high frequencies, right? And by adding this gain plot to the existing plot from filter and PWM, we can get, or we can satisfy the open loop stability criteria. Again, namely high gain at low frequencies, low gain at high frequencies. And by doing so, we can also have a crossover frequency, right? Before there was no crossover frequency, but with the addition of the compensator, you can get a crossover frequency from which we get the phase margin, right? Okay, so then we went through the method on how to design the type 2 amplifiers or type 2 compensators, right? I won't go through those anymore. Excuse me. And then also we learned about another criteria, which is called the slope criteria, right? -1 criteria, meaning at crossover frequency, it would be nice to have the slope at -1. Reason being, if the slope is at -1, then the fluctuation in the phase angles that would affect phase margin would be much less, like such as this, right? You can see the drastic change if you have a slope -2 or -2 slope. You can see that it depending on the damping ratio, which would typically be very low at heavy load, you can see the drastic change in phase angle. That would not be good for phase margin. Whereas if it's -1 slope, you can see the fluctuation in the phase angle is not as much, right? It's almost very gradual, right? So that will be beneficial for keeping a stable phase margin. All right, so we did this, and then so we've done discussing where to place crossover frequency, if there is ESR, if there is no ESR, right, to meet that -1 criteria. If there is ESR right there, then you place the crossover frequency right after the ESR frequency, right, such as here. That way, you can see at crossover frequency, the slope is -1. It's one of the objectives in compensation. Okay. This one is exactly the example with ESR, right? You can see that I place the crossover frequency after ESR, right? Now, let's move on to the next topic. Okay, once we're done with type 2, then we also have this different type of compensator called type 3 compensator, right? What is a type 3? Sorry, what is a type 3 error amplifier or compensator? It is the type that introduces double equals zeros and double equal poles. You'll see soon the reason why we want to add double equal zeros and double equal poles. That's different from type 2, right? Let me show you the graphs first. Right here. Right, this is type 2, right? You can see in type 2, we introduce one zero, one single zero, and one single pole, right? By doing so, right, the most I get in terms of the additional phase angle will be 90 degrees because that's a single order circuit, right? So 1 0 gives you a plus 90 degrees, right? So the max you can get in terms of boost in the phase angle is 90 degrees if you use type 2 amplifier, right? However, if you feel like this boost of phase angle, again, this would help in phase margin, right? If that's not enough, especially if you come across different cases, I'll go over those different cases later. Sometimes you need additional boost in the angles. In other words, 90 degrees may not be enough. You might want to have 180 degrees, phase boost, such as that. So how do you do that? Well, you can get it by, instead of introducing one single zero, you can introduce you can introduce double zero, right? A double zero means the maximum angle you get is 2 times 90 degrees, right? So that's 180 degrees. So it looks something like this. So again, you start from high gain at low frequencies with a -1 slope, and then right at this corner, you turn the slope, right? Instead of going flat like before, see that before it's flat, right? After the corner there is flat. What if you add 2 zeros, right? Again, why? Because by adding 2 zeros, I can get up to 180 degrees boost in phase angle. Right? Now, if you add 2 zeros, that means the slope, if you start from -1, if you add 2 zeros, then you're going to end up with +1, right? Because remember, a zero introduces +1 slope, right? So 2 zeros gives you +2. So -1 plus 2 gives you +1, right? And then at the other end, we introduce 2 poles, right? Why 2 poles? Why not 1? Well, because if you do 1, again, if you calculate the slope, right, it's starting from +1. If let's say you introduce 1 pole, that means what? That means this is going to go flat, right? If it's going to go flat, that's not going to be good for the high frequency gain. Sorry, it's not going to be good for the high frequency gain. Right? Remember, high frequency gain, you want it to be low, right? So flat is not good to do that, right? So we want to have a negative slope. So therefore, in order for us to have a negative slope, you need at least 2 poles right here, right? So 2 zeros over here, 2 poles right there. That way, you start from +1, and then with the 2 poles, that's going to be -2. So +1 minus 2 gives you -1. So this will be good because then it will give you that a low gain at high frequencies, right? But the important thing here is that with a type 3 compensator, you have another extra 90 degrees of a phase angle, right? Again, because because you add 2 zeros. That's why you can see this value is bigger than type 2, right? Any questions so far, conceptually? All right. Go back here. So again, introduces double equal zeros and double equal poles. Now you know where they at, right, in the gain plot. Right. Again, the double equal zeros gives you the +1 from the -1 at low frequencies, and then the double equal poles gives you the -1 after after the double zeros. All right. This is how the circuit looks for type 3. Okay. How is it different from type 2? Anybody can answer that?
It
How's it
has
different?
the capacitor and resistor on top of R1.
That's correct. This is the extra part right there, right there. Okay. Now, when you implement this, it will look something like this. So here's the controller IC right there. Has the VC pin, right? Has the FB pin, right? And then, yeah, so you just need those 2 pins basically to implement this compensator, just like type 2, same way, right? Except now you add a parallel branch across or in parallel with R1. Now go ahead and compare the 2 pictures. I'm going to make it smaller. Maybe, yeah, right there. Okay. Now look at R1 right here, right? Compare that to the one over here, right? So where is R1 in the actual implementation? Where is R1?
R top, right?
R top, exactly. So you can see that R1 is actually our R top. What is R top? Well, that's our voltage divider, isn't it? Remember our voltage sensing, right? That's our output voltage. That's tied to the actual output terminal, right, of the DC to DC converter, and this will be our voltage sensor, right, the voltage divider. So you can see the reason why I want to show you this, because now you know that, let me erase, that out of these 2 resistors for the voltage divider, R top and R bottom, which one affects the loop of the system, the loop stability of the system? Is it R top or R bottom? Now you know which one, right? By comparing the first picture and the second picture, I know right away that R top is our R1 here, right? So therefore, as you can see, R1 is part of the control loop. R bottom is not. See, this R bottom is not, right? You don't see our the resistance that represents our bottom here, right, in this picture. Nothing there, right? So that would be important for you to know, right? So again, it is important to know why. Well, because again, R top affects stability, right? It affects the gain actually, right? Our Z2 over R1, that's the gain of this op-amp, right? So you can see when you select voltage divider, right, when you're designing DC to DC converters and you close the loop, make sure that you pay attention to R top, right? Make sure that the one that's going to be fixed is R top. Because remember, in EE411 or 410, don't remember which one now. You should get a good enough ratio to give you a very accurate output voltage sample, right? Let me just write down the equation. If this is VFB, which it is, right? VFB, we know that VFB is equal to V out times R bottom over R top plus R bottom, right? Okay. And then let's say that feedback is, I don't know, 1 volt, and V out is, let's say, 12 volts, right? So from here, you see you have to find a good ratio, right, for R bottom and R top, right? And let's least likely you're going to have R top and R bottom. There are standard values, right? So which one of the two you should choose as a standard value resistor? Now you know. Now you know that if you're designing or you're choosing R bottom and R top, you want to make sure that R top is the one that should be the standard size or the standard value, right? R bottom, right, is the one that that would adjust, right, to give you the right ratio. So you can make this R bottom a potentiometer, right? Okay, because that way, as you are changing R bottom, you're not changing the loop, right? Because this is fixed, right? This is already fixed. So you're not changing R top. That's what I'm saying. Okay. Anytime you come across this issue of selecting R top and R bottom, make sure that R top is the fixed value. R bottom is the one that you can change around. Is that clear? Right. That way you're not again affecting the loop stability. Okay. Any question on this? What would we need type 3? There are many instances where 90 degrees of phase boost, such as that introduced by type 2, is not enough to compensate for the phase lag through the modulator or plant. Right? For example, cases such as, I think I mentioned one already on Monday. If let's say the ESR is really small, right? So the ESR really small means what? ESR is way above the crossover frequency, right? Imagine this picture right here, right? That's the ESR frequency. What if the ESR is somewhere over here, far away, right? Then it will be hard for you to select crossover frequency, right? That has the -1 slope. Remember that ESR gives us this -1 slope, like that's a 0. Right? This is -2, now it's -1. That's why you pick the crossover frequency after the ESR frequency. But what if that ESR frequency is far away from this corner frequency, right? And then it will be hard for you to choose the crossover frequency, because as you are increasing the crossover frequency, let's say you want to select the crossover frequency to be closer to this far away ESR 0, then this crossover frequency is becoming closer and closer to switching frequency, right? And that's not good, right? You want crossover frequency to have a good distance from the switching frequency. All right, is that clear? So this one case where we're gonna need to use type 3, because then imagine if this is all -2 slope. Oops. Something like this, right? Forget about this. Then now you can still place your crossover frequency away from switching frequency, but then you just have to change the compensator to type 3 instead of type 2, right? Okay. Any questions? Okay, notice that if you do type 3, look at type 3 again, right here. Look at this one. Look at the crossover frequency. See this? Right? So the crossover frequency has a +1 slope, right? So if the initial gain plot has -2, right, has -2, then -2 + 1 gives you -1, right? Gives you -1, right? So that's why you need the type 3 amplifier. Just like this example I had earlier right here. You see, imagine if this is -2, and then you add type 3, then you're gonna add +1 to it, right? So then you're gonna end up with -1 slope at crossover frequency. Is any of this confusing to you, or you're still okay? All right. So that's one example where you need type 3. For cases where there are two reactive elements in the plant, an electrical system with LC filter, just like a buck converter, the phase lag through the plant can approach 180 degrees because that is a second order system. And hence a substantial boost is required in the amplifier to maintain a reasonable phase margin. So if you start with 180 degrees already, right, because of 100 LC filter, then you definitely need a good boost in the phase angle, right? And this is the case I just explained earlier. When you have low ESR output capacitor, then type 3 would not rely on the location of the ESR 0, right? Because again, type 3 would introduce you to the +1 slope. So the overall slope will be -1. Any questions? Determining whether to use type 2 or type 3 may also use the ratio. So this item or this bullet basically states that how do we determine when to use type 2 or type 3 if, let's say, it's neither one of the two cases that I just explained to you. Well, you can apply this method, right? This is called FESR over FLC method, the ratio basically, right? So first you calculate the double frequency, the corner frequency basically of the filter, the LC filter, right? You learn from circuit class, that's how you find the corner frequency of the LC filter, right? The output inductance, output capacitance, right? And then you also calculate the frequency of the ESR, the zero frequency of the ESR, right there. And then you compare the two, right? The ratio, that's what you're getting. If the ratio of ESR frequency to corner frequency of the filter is equal to or greater than 5, then use type 3. If it's less than 5, then use type 2. But this is a rule of thumb, right? And even after you've done this, and then you build the prototype, and it seems like type 2 is not sufficient, doesn't give you sufficient phase margin, then you can always go ahead and add the additional branch, right, to include in type 3. Remember, for type 3, all you need is to add this branch. So you can start from type 2. That's type 2, right? So ignore this. So you can start from type 2. If you find out that that's not enough, that doesn't give you enough phase margin, then you add this, right? So that's probably why it's wise to, if you're not sure, it's wise to provide like a pad, what do you call it, like a trace on your PCB, right? Just in case you need it. So this trace right here, right? So at the beginning, you don't use this trace, and then there's a pad for the resistor and capacitor, right? Just leave them empty, right? So you start from type 2, and then if you find out, oh boy, type 2 is not enough, then you can start, placing resistor and capacitor in the pad that you provide already. Okay. Any questions? So those are mostly concepts, right? Do you understand the concept now, hopefully, of why we need type 3? Any questions? All right. Component selections, referring to type 3 plots at some point of FZ. Do I have a plot? Yeah, right here. Yeah, right there. That's FZ, right? The 2 zeros, and there's the 2 poles, right? So referring to this figure, before I do that, just one more time, okay? This just to make sure that we're on the same page. This first plot right there, that's what happens without the compensator, right? That's the reason why we need compensator. And then the red one is what we want, right? That's what we want the open loop gain plot to look like, right? In order to get that red one, the red plot, I'm going to need type 3. Okay. Notice that the ESR 0 is far away, right? It's far, so well, relatively speaking, it's kind of far from the corner frequency, right? So just in case this is too close, if this location is too close to the switching frequency, then it is not good for you to pick crossover frequency over here, right? Or after the crossover frequency, right? Make sense? So this is an example where we use type 3. So again, FZ is right there, FP is right there, right? And the crossover frequency is right there. And okay, referring to that figure, at some point FZ less than F crossover frequency, the gain curve must be turned around to proceed upward at +1 slope. So it starts from -1, but we want it to proceed with +1. This is done by providing two zeros at the same frequency, right? And then at some point, FP higher than F crossover frequency, the gain must be turned around to proceed downward at -1 slope. This is why we need the double pole, right? As I explained earlier. The phase lag through type 3 amplifier at the crossover frequency, right? It would also depend on K. Remember K? K is the ratio of the crossover frequency to the zero frequency, as well as the ratio of the pole frequency to the crossover frequency. The same definition as you already had from type 2. The same equation, the same ratio. So again, depending on the ratio, which physically means how far you want the crossover frequency from the right here, right? Let me just. This is the crossover frequency. Depending on how far the zero frequency is from the crossover frequency, that's actually not the crossover frequency. Hang on, sorry about that. Let me scroll down. There. Here's the crossover frequency, right? So depending on how far you want to select the crossover frequency from the zero frequency, as well as equal distance, right, to the pole frequency. That will determine the amount of phase angle, phase lag. Okay, that's what we call K, like the ratio of the two frequencies. Okay, the smaller the K, the bigger the phase lag. Right? The bigger the ratio, the smaller the lag. Right there from this table. And so this is similar to what we did for type 2. Again, the op-amp circuit looks like this, right? And then the transfer function of type 3 would be this long transfer function, right? Okay, you can see we have two zeros, finite zeros, one pole at the origin, which is right here, one pole, sorry, two poles, two finite poles, right? So two finite zeros, 1 0 at the origin, and two finite poles, right? So 5 total, right? In the above circuit, you need to choose, just like type 2, remember type 2? We want to place the 0 before the pole, right? So in order to ensure that the zeros occur before the poles, then you have to select the components carefully. In this case, R1 must be larger than R3, and C1 must be larger than C2, right? Location of poles and zeros. The frequency where the impedance of R1 is equal to that of C1 plus C2, R1, and then C1 plus C2, right there, right? Yields a pole at close to the origin. So that's the one that's going to be responsible for the pole at the origin. This one, right there. So that would give us the initial -1 gain, right? Let me just show you again, just make sure that you know what I'm talking about. That would give us the right here, the -1 slope. So there's going to be a pole at the origin, right? That's why you get -1 slope. So it comes from R1 and C1 and C2. So right here, that's the location of that pole, as you can see. The frequency where the impedance of R2 is equal to that of C1 yields the first zero at frequency. So this one basically. That's going to be the first zero. I call it Z1, the first zero frequency. And you can see there's a second zero, R1, R3, and C3 right here, right? Let me, well, get the idea, right? That's the second zero, and that's what I have right here. Same thing, right? And then what did I say here? The frequency where the impedance R1 plus RT is equal to that of C3 yields the second zero at frequency of FZ2. And then it says, or the equations here, looks like this equation right there is approximately equal to 1/2 pi R1 C3. Why is that? Because over here at the beginning, I put the condition that in order to ensure that that zeros occur before the poles, right? Then you need to have R1 much larger than R3 and C1 much larger than C2. So since R1 is much larger than R3, therefore this equation right here is approximately equal to 1/2 pi R1 C3. Any question on this? And then now we going to the poles, right? The first pole. The frequency where the impedance R2 is equal to that of C1 plus C2, that must be the first pole, right there. Where is it? Right here. Right. That would give us the first frequency of the pole, right there. Right. So now you can see the equation. The actual equation is this, and then I put approximately equal to 1/2 pi R2 C2. Why is that? Because at the beginning, I put this condition that C1 must be much larger than C2. If C1 is much larger than C2, that means this would be approximately equal to 1/2 pi R2 C1 C2 divided by C1, right? So C1 plus C2 is approximately equal to C1 because C1 is much larger than C2, right? So C1 cancels, and now you have this frequency for the first pole. The second pole, right, that's from the last term, right here, right? That's from R3 and C3, right there, okay? Any questions so far? Again, we want the two poles to be at the same frequencies, right? The two poles, the two zeros. Remember, we have FG1, FG2, FP1, and FP2, right? Two finite zeros and two finite poles. And for type 3, we want the location of these two zeros to be the same frequency. Same thing with the poles, right? So we have double zero and double pole, right? Double zero, double pole, right? Make sense? So that's why you need to set the equation to be like this, that FZ1 equation must be equal to FZ2 equation, and FP1 must be equal to FP2, right? Because frequency, I should say, right? The frequency of FZ1 should be equal to FZ2, and FP1 should be equal to FP2, right? And of course, the implication will be when you choose the values, right? And before you choose the value, you have to set the equation to be this way. The location of the double zeros and the double poles will be fixed by the K factor, as we talked about earlier, just like we did it for type 2, right? So that we can get the desired phase margin. So here's the possible scheme for finding component values. Right? Let's say You want to, how many values do we need? Let's check. 1, 2, 3, 4, 5, 6. So I have R1, R2, R3, C1, C2, C3, right? So 3 resistors, 3 capacitors. How do we get R2? So this is just one way, one method to size those components. Choose R2. So you need to choose R2, from which you'll get C1 and C2, from FZ1 and FP1. You know what FZ1 is? That's the desired frequency of the zeros, and FP1 is the desired frequency of the poles. Right? That's from K. So should be more specific. First, you choose crossover frequency, right? You choose first you choose this, and then you choose K. What is K? This ratio right there. I need to make sure that I put the right ratio. So FC not to FC. Okay. Right, and then FC not to FZ. That's your K. Right. So choose FC not, and then choose the crossover frequency and choose K. Right. That's one method. And from here you get the desired FZ right there, right? So that means FZ is equal to FC naught divided by K. Likewise, K is also equal to FP over FC naught, right? If you already picked K, then you know that FP, the frequency of the poles, must be K times FC naught, right? So choose these two, and then you also choose R2. So choose 3 values: crossover frequency, K, and R2. How do you choose crossover frequency? Well, we already talked about it on Monday as well, right? This would be an order higher in magnitude with respect to the corner frequency of the filters, and about a fifth, right? Compared to the switching frequency, 1/5 of the switching frequency, right? So that's how you would select FC naught, right? And then K, you can just select maybe K equals to 2 or 3 for now. It doesn't really matter, right? Because that's going to be iteration after this. And let's just pick K equals to a value, again, by having that value from the table, of course, right? Right here. Oops. Either 2, 3, 4, 5, or 6, right? So just pick one value, maybe the midpoint. I don't know. It's up to you, right? And then once you get K and FC naught, you get FZ and FP, and then you pick R2, and from there, I know FZ, I know FP, I know R2, then I can solve for C1 and C2. Agree? Or any questions? All right. Okay, and then so C1, so I have R2, C1. You know what? Let's do it this way. I need to find R1, R2, R3, C1, C2, C3, right? So I pick this one, and by doing so, I got our C1 and C2, right? So once C1 and C2 are obtained, then calculate for R1 from the following equation. You already know what FP is, right? And then you get R1 from this equation, right there. C1 and C2 is already known, FP is known. So then R1 now can be calculated. Okay. And then once R1 is found, you can then calculate for C3 from this equation. Again, I know FZ, right, from here, right? FZ we know, R1 we already found, and then the only unknown is C3. So from this next equation, I get C3. right? So only one left, right? R3. Where do we get R3? From the last one, from the pole right here. FP2, again, you get it from here, right? You know FP2, you know C3. The only one unknown is R3, right? So you get R3 from here. Okay. Then once you get all these values, what do? You simulate, right? You simulate this compensator, right? And then see how much phase angle you get. If it's not enough, then increase K, right? And so on and so forth. Any question on this? Again, this is just one way, one method to do this, right? As you can see, you can do different methods, right? Depending on which you initially choose, right? In this case, I initially chose R2. Any questions? So we're done with that chapter, right? Let me go to the table of content. So we've done chapter 7, right? Chapter 8, chapter 9. I'm starting from the last 3, and then we're going to go back to the beginning of the book. However, if you look at chapter 1, is on linear regulators, and chapter 2 is on switching regulators, and chapter 3 is on charge pumps, right? Out of those 3, I would start with charge pumps first, because I know that you've seen linear regulators before, right? You've seen switching regulators before. However, if you have some spare time, please go ahead and go through chapters 1 and 2. I will get back to these 2 chapters if I have the time this quarter. But especially if you didn't take 410, 411, I think these first 2 chapters will be a good background information on the remainder of this book, starting from chapter 3, right? Okay, so I would like to go over some new materials, right, that you have not seen before. At least majority of you maybe have not seen before. So that will be charge pumps. So I'm going to start with that topic. Again, hopefully I have the time to cover chapters 1 and 2 toward the end of the quarter. If not, then yeah, no worries. I think you've seen it before, right? Okay. Now let me just go through the chapters real quick. You can see that's chapter 1, the basics, intro to linear regulators, right? Basic operation, right? Advantages, disadvantages, right? So I think it's pretty light reading for you. Disadvantages, right? And how do you apply it in power supply, as an example, with the headroom loss. And you have these load dropout regulators, right? Basic information on LDOs, how it works, or how is it different from the linear regulators, right? Then you have the voltage regulator design, right? The tricky part here is the capacitor sizing, I believe, right? Single phase rectifier with linear regulator, if you combine them both, right? Input output capacitor sizing, transformer if you need to use the transformers. Again, I'll go over this if I have the time. Okay. There's a different type of regulators, Zener regulators, right? So in case you ever need to use Zener or shunt regulator, here you have the reference here. Okay, that's basically chapter 1. And then chapter 2 is on switching regulators, right? So I start from linear and then move on to switching, right? From linear to switching. What is the difference between linear and switching, right? So we just use a switch instead of a drop, sort of using the solid state device as a resistor or a drop, a voltage drop, right? Why don't use it as a switch, right? That turns on and off. And you can see the progression of how it becomes a switching regulator from a simple switching circuit, advantages, disadvantages, right? Okay, again, most of these are background information on switching regulator, right? So it's not like in EE410, we go into the design, right? We go into the component sizing, detailed discussions of switching regulator. These are just mostly background information on a switching regulator. All right, we'll skip this. All right, so then chapter 3 is going to be on a different type of DC to DC converters, right? So this is the topic that I did not cover in EE410, 411, but it is another type of DC to DC converter, right? It's called charge pumps, and this type of converter does not use any inductors. Right? The one that you learned in EE410 is inductor-based converters, right? Buck boost, push-pull forward, single switch, push-pull forward and fly back. Those require inductors, but charge pump does not, right? So in this inductorless DC to DC converter, capacitors are used to transfer energy instead of inductors. The pros would be no inductor. That means it can actually be small, right? More compact. It doesn't have any inductor. The cons would be it acts like a current source, so load current needs to be present, right? And then limited output currents require large capacitors even for small currents, because if you compare the two between inductors and capacitors, of course, capacitor would have a more limited capability to provide currents than inductor. Practical uses. High side, this is one application example of charge pump, is to be used as a high side and channel driver, since the gate must be driven to potential higher than the drain supply. Otherwise, you would have to use a separate supply, right? So it's a high side, like in a buck converter, right? You have a high side and you have a low side switch, right? So to drive the high side, you could have this node right here has to be less than this node, right? The gate has to be higher than the source. So you can always implement a charge pump to make sure that the gate is always larger than the source, right? And then RS-232 level shifters, where they are used to derive positive and negative voltages, often plus minus 10 volts, from a single 5 volt or 3 volt power supply. And then you can also use charge pumps in LCD or for LCD or white LED drivers, generating high bias voltages from a single low voltage supply, such as battery. So from a battery, you boost the voltage up, right, using charge pump to drive LEDs. Dynamic gate biasing. Some of these I'm not even familiar with, such as this one. Dynamic gate biasing, where uncontrollable charge pump circuits are used for the stable biasing of MOSFET gates. That's from this reference. So, I don't know in details what this means. CMOS front-end optical preamplifier and in low voltage continuous time. Bi-quadratic filter applications, whatever it is, it's just an example that I found from these different references that make use of charge pumps, right? That's another example where we can use charge pump to generate the higher than normal voltages required to write or erase information in non-volatile memory circuits. Like EEPROM and flash memory devices require a high voltage pulse to clean out any existing data in a particular memory cell before it can be written with a new value. Early EEPROM and flash memory devices require two power supplies, +5 for reading and +12 for erasing. Now they require only one external power supply, either 1.8 or 3.3, and use charge pump to get a higher voltage to erase cells. But then that higher voltage is generated internally by on-chip charge pump, right? So the high voltage, you get it from the charge pump. Charge pump design guidelines. Assume 50% duty cycle, square wave, AC waveform. Output capacitor must provide total load current for half of the cycle. Circuit resistance must be small so that capacitors charge completely, and charge time will be about 5 times effective circuit time constant. Here's an example of the first charge pump circuit for this book. Here I have double voltage doubler. So the input, which is right here, the output, which is right there, and the output should be close to double the input, right? So the maximum you can get on the output is twice the input. But you'll see later that you could never get twice the input, right? Because in order to do that, you need like a huge, which I believe C2 capacitance, right? So it's not practical, basically. But theoretically speaking, you could get output voltage that is double the input voltage. Okay? How? Again, you can see that there is no inductor here. There's only diode. There are only diodes, capacitors, right? And we have the switch as well, right? The switch is right here. Of course, in practice, this would be MOSFETs, right, or solid-state switches. This is just to illustrate how the circuit functions. All right. The objective is to charge C1 from the supply. So first you charge C1 from the supply, and then transfer its charge to C2. And then once you get the energy to C2, then you release it to the load, right? So since C2 is referred to VDD, VI will be greater than VD. If you look at the circuit, right? If you can somehow get some voltage, whatever voltage, right? Just call it V, or what do you want to call it? Vx, right? You can see by KVL, right? Look at this loop right here. Let me use red. Whatever that Vx is, if you go around this loop right there, notice that VDD plus Vx is equal to Vout. See that? That means Vout is larger than VDD because you have some extra voltage there across the cap, right? So you have a step up basically, right? But again, in theory, this is double the output voltage, double the input voltage in theory. But in general, you can see that Vout is larger than the input. Okay. Any questions so far? So that's what I meant by since C2, the second bullet down there, since C2 is referred to VDD, Vout will be greater than VDD. The switch is first connected to ground, charging C1 through D1 to the supply voltage. Next, the switch is toggled to supply, and hence C1 dumps its energy through D2 into C2. The process is repeated, and C2 will eventually charge to a potentially equal to VDD, lifting Vout to 2 times VDD. I should not erase that. Oh. So imagine if I have eventually, right, steady state, I have VDD here, which is the same as this, right? Again, by going through the KVL, you can see clearly that Vout will be twice the input, right? VDD plus VDD. Right. Okay. let's go through the steady state analysis of this circuit. So, how do I do this? Sorry, let's do it this way. When the switch is low, connected to the ground, so you can see that two positions of the switch, either low or high. Okay, so right now, the state of the circuit is I'm going to connect the switch to low. Right there, right? So if I connect the switch to low, this is where I need to go back and forth.
What is it?
Right here. I hear my echo. Somebody turn off the microphone. Thank you. Okay, so here, if it's connected to the low, right there, right, then what's going to happen? Then go ahead and look at this loop right here. You have a loop thing, right? And you can see clearly that VD1 must be reverse bias, right? Oh, sorry, reverse bias must be forward bias, right? Minus plus, plus minus, plus minus, right? So VDD is equal to VD1 plus VC1, right? Of course, when you first start the process, C1 is already discharging, right? So its voltage is going to be lower than VCC. And so that's why you have positive voltage across the diode. And so therefore, the diode turns on, right? Diode turns on, and we have the circuit right here. There, okay? So on C1, what we're doing now is that since diode D1 is on, we are charging C1. See that? We are charging C1. So VC1 charges to VDD minus diode. So if there is a voltage across the diode, then at the end of the transition, voltage across C1 would be VDD minus V diode D1, right here. So call it equation 3-1. The charge absorbed by C1 is equal to QC1. So the amount of charge that is being transferred to C1 is called QC1 right here. That is equal to Q low. Why Q low? Because the switch is at the low position. Right? So Q low, the amount of charge during the low state of the switch, is equal to I times delta T. Remember, Q is equal to I times delta T, right? Delta Q. So you can see that during the time when the switch is at low, the amount of charge is equal to the current right here, which is what we call I sync. So there's one current right there, right? That one current is equal to I sync times delta T. So delta T, in this case, I call it tau low, right? So the amount of time that the switch is on the low position, which should be 50%, half of the cycle, right? Make sense so far? I'm doing this slowly. All right. So now I have the capacitor C1 charge to this voltage, right? VDD minus V diode. Then what happens when I do the opposite? What if I turn the switch high, right? Instead of low, now we connect it to the high side, right there. What's going to happen? Let's see if I have the circuit. Well, let's just go back to the circuit. When it is at high side, right? Right away you have this loop. You see this loop right here, right? This small loop. So by KVL, VC1. So if this is plus minus, right? Because that's the anode, that's the cathode. VC1 is plus minus plus minus. VC1 plus VD1 equals 0. Yes? Just this loop right here. If that's the case, then VD1 is equal to minus VC1. You see this minus sign, negative sign? So that means I know that as soon as I connect the switch to high position, then D1 turns off. Right, D1 turns off. Any question on this one? Now D2, I believe, is a bit trickier. D1 is easy to see, it's reverse bias. D2, let's see D2. The anode is right here, has connected to the same voltage as the voltage C1. That's the loop right there. Okay. Here's the loop. Let's see if I can use that loop. That would be what? That's VC2 minus plus. Okay, plus minus, minus plus, minus plus. What is that? So let's see. VC1 plus minus, minus plus, minus VC2 minus plus, minus VD2 equals 0. Yes? So therefore VD2 is equal to VC1 minus VC2. Agree? All right. Now, VD2, not VD2, VC1, when I turn the switch on to the high side, what was the voltage on VC1? It was VDD minus V diode, right? Remember earlier? Right. So now we have VDD minus V diode 1. Right. That's how much voltage we have across VC1 right now. Okay. Minus VC2. So now it's a matter of how much is VC2. Remember earlier I said that eventually this is going to be VDD, right? But as I'm charging capacitor C1, VDD, sorry, not VDD, VC2 is actually delivering energy to the load. Discharging, not charging, discharging. So during the time when the other half of the story that I didn't say, that I didn't explain, is that during the time when the switch is at low, this capacitor C2 is discharging to the load. Oops, sorry, discharging to the load. Right there, right? So if it's discharging, that means this voltage is decreasing, right, from VDD. So right now, let's just assume V diode is 0, because that makes it confusing. Let's just assume V diode is 0, right? So no drop across the diode. So now when the switch at the low position, C1 eventually is going to be VDD, assuming V diode is 0, and C2 is going to be less than VDD, right? Because it's being discharged right now, right? So the capacity is being discharged from positive VDD to, of course, it's going to be less than VDD. So let's go back to that point right here. So if I assume VD1 is 0, so that's going to be VDD minus a voltage that is less than VDD. That's why determining D2 is a bit tricky, because I have to explain what's going on with C2. So what do you get if you subtract a number that is smaller than VDD? Then you get a positive value, right? So that means D2 is forward bias, because it's positive, right? It's positive value. Again, because voltage across C2 should be less than VDD by now, whereas voltage across C1 is at VDD, assuming diode is 0. Any question on this? Now, maybe you can find a different loop to explain this, but the loop that I'm using is this loop right here. Where is it? Where's the loop? It's this loop right here, isn't it? Yes, this loop. There is a different loop. What is a different loop? Yeah, there's another loop actually. Maybe that's easier to see. The other loop would be, so the first loop that I use is this. Let me just show you the loop that I did. Is this small loop right there. Right? That's how I explain it over here, right? Not that straightforward, but let's try a different loop. Let's see if that's more straightforward to explain why D2 forward is forward bias. So I'm using this. Oh, I don't know. What is it? I lost it. Oh, here. That's a big loop. That's a much bigger loop. So if I do that loop, if I choose that loop, let's check it out. If the equation is too long, I'm not going to do it. Let's see. Correct me if I'm wrong, okay? This is just going over this loop with you, see if it makes more sense. So VD2, starting from VD2, starting from that point, plus minus, and then I have plus V out, plus minus, and then I have minus plus, minus VDD, and then I have minus plus again, minus VC1, and then that's it, right? Equals 0. And we know at this point, VC1 is roughly equal to VDD. Right? All right, so VD2 is equal to, that's 2 VDD, isn't it? So that's going to be 2 VDD minus V out. I don't know. This will also work. Because this tells me that voltage across D2 right now is equal to 2 times the input minus the output. As I said earlier, right? V out could never be higher than 2 times VDD. In theory, yes. Even in theory, if it's equal to 2 VDD, if let's say this is equal to 2 VDD, then what happens with VD2? That's equal to 0, isn't it? 0 means it's a short or on. I like this better actually than the first smaller loop. But in general, V out is going to be less than 2 VDD, right? In general, V out is going to be less than 2 VDD. If that is the case, or there you go, less than or equal to VDD. If that is the case, then VD2 is going to be 0 or larger than 0, right? It's going to be like this. Yeah. Since there. What do you think? Which one do you like? I like this one better. It's a longer loop, but it's clearer to me than doing the small loop. Well, it's up to you. I have the explanations for both. If you want to screenshot this, go ahead and do that. Actually, I'm going to include this in the future version of the book. So I have the 2 version of the KVLs. Right. Any questions? All right, not. Let's go back to here. Actually, this is the equation, isn't it? Oh, I don't know. I don't think so. Oh, maybe. So when the switch is high, connected at VDD, D1 is off and D2 is on, as I tried to prove earlier, right? D1 is for sure is off, and D2 now we know is on. Charge from C1 is now transferred to C2, right? From the low capacitor to the high capacitor, right? So the charge transferred to C2, and then C2 charges to right here. So the C2 charges I'm using 3.1. V out is equal to, there's the equation for V out, right? Charges from C1 is transferred to C2, C2 charges, and using 3-1. I believe this is the, which loop? Is that the same loop I did earlier? It is, right? It is, yes. So from that same loop, that big loop right there, The equation is V out is equal to VDD plus VC1 minus VD2. And remember VC1 from the previous state is equal to VDD minus V diode, right? So at the end, you have V out, the equation for V out equals to V2 VDD minus 2 V diode, right? So this is another proof, right? That if V diode is not equal to 0, then V out is always less than 2 times VDD, right? This proves, right, if that V out is less than or equal to twice VDD, right? Depending on V diode. If V diode is 0, then it's going to be equal to 2 VDD. If V diode is not 0, it's going to be less than 2 VDD. Okay, so the amount of charge that is transferred to C2 will be the same as the amount of charge that is being transferred to C1, right? Earlier. So QC2 is equal to Q high. That's equal to I source. So the current that I call for the second state right here. So you can see now C1 discharges through D1 this way, right there. And you can see that the current that I have right here, I call it I source. So sourcing the load. All right, so that's I source again. I'm trying to find delta Q is equal to I delta T, right? Since this is corresponding to high when the switch is high, so therefore this is going to be Q high or QC2. That's going to be I source times tau high. What is tau high again? That's how long the switch is on the high position, right? So far so good. The total charge delivered to the load terminals would be Q load, right? So the load itself should have current all the time, right? Because it's a load, right? It requires current all the time, right? So you have the charge pump and you have the load, right? If there's a voltage here, then of course there's always going to be current flowing by Ohm's law, right? So throughout the entire period of the switching, there's always current flowing through the load, right? So therefore, the total charge received by the load should be equal to I load times the delta T, which is the entire period, tau high plus tau low. Any question on 3-3? In steady state, the amount of charge transferred to C1 during tau low must be the same as the charge transfer from C1 to C2 during tau high, right? Which makes sense, right? Energy transfer to C1, and then C1 transfer to C2, all the while, the entire charge must be used by the load. So therefore, Q high is equal to Q low, right there. And the equation for Q high earlier is I source times tau high. Q low would be I sink times tau low, right? From here, I get the ratio. That ratio of tau high over tau low is equal to I sink over I source, right? And again, this charge right here should be the same charge that the load will receive. Right? That's why I have right here, Q load should be equal to Q high, it should be equal to Q low. And the equation for Q load is I load times tau high plus tau low, right? If I set it to equal to Q low, then Q low is I sink, right, times tau low. And tau high plus tau low, that's equal to T, the entire period, right? So from here, I get the relationship between I load and I sink. See that? And then that's written here. I load should be equal to I sink times tau low over T, right here, right? But again, I sink times tau low, that's equal to I source times tau high. So I can also have another expression for I load right there in terms of I source instead of I sink. So far so good. So this is that's how you can find the current, the load current in terms of I sink and I source. You can see there's duty cycle here, right? I don't know if you see it. Oh, yeah, there is a duty cycle right there. Okay. The amount of charge transfer from C1 to C2. So this section is on sizing the capacitors. How do you size the capacitors C1 and C2? Right. Eventually, you're gonna need to know how to do that, right? Just like sizing L1, right? In buck boost or buck boost. So how do you size capacitor C1? The amount of charge transfer from C1 to C2, that is doing tau high, isn't it? So when the switch is on the high position, that's when we transfer from C1, or charge from C1 to C2, right? The amount of charge that is being transferred is called delta Q, is equal to Q start, the beginning of the transition, and minus Qn, the end of the transition. So right when you change the position of the switch from low to high, that's Q start. That's the beginning charge of the capacitor C1. And then Qn is when you start moving the switch to the low position again. Right. So Q start is the amount of charge at the end of tau low when C1 is about to transfer its energy to C2. From figure 3-1, VC1 start is equal to VDD minus V diode. Right, that's the small loop right here. It's the one I showed you earlier. It's kind of clouded right here. This loop, oops. This loop right here. Right. Okay. Let's go back. So VC1 start is equal to VDD minus V diode. That's Q start is, remember, Q is equal to C delta V, right? Or delta Q is equal to C delta V. Delta Q is also equal to I delta T, right? So here I use Q is equal to C delta V. C1, that's what I'm looking for. Delta V is the voltage at the starting point of the transition. That's VC1 start, right? So therefore, if I replace VC1 start with this equation into here, then I get this equation right here, right, for Q start. What about Qn? From figure 3-3, again, that's the long, remember this is the big loop that I wrote earlier, right? From the big loop, I know VDD plus VC1N minus V diode minus V out is equal to 0, right? That big loop again. Oops, this big loop, where is it? Right here, that loop right there, see this? Right there. So if you use that loop, that's the KVL. Oh, what is it? Right here. That VDD plus VC1N minus V diode minus V out is equal to 0. So therefore, VC1N is equal to V out plus V diode minus VDD. Check my algebra. I think that's correct. Right? Yes. All right. So then I have VC1 start and then VC1N. Right. Sorry, Q start and Qn. All right. And then delta Q, I have Q start and Qn. So therefore, going back to the beginning, right, delta Q is equal to Q start minus Qn. Now I can just plug in those equations for Q start and Qn. And I have this equation right here, right, from which I can rewrite, right, simplify the equations. Or I get delta Q equals C1 2 VDD minus V out minus 2V diode, right? And then recall that delta Q is the charge transferred from C1 to C2, which has to be equal to the charge transfer from VDD to C1 during tau low, right? So when I turn the switch to low, that delta Q is the same delta Q that I transferred to C1 from the source, right? So Q low is equal to delta Q, and remember delta Q low, the two equation is I delta T equals to C delta V, right? So that's the I during Q low, during low. That's the T for the low, right? And then that's C1, right? That's that we are charging during the time the switch is at the low position. And delta V is the voltage that we have from the previous equation right there. Actually, that's delta Q. That's delta Q equation. That's the delta Q equation right there. Let me scroll down, or scroll up a little bit here, right? So that same equation right here is equal to I delta T, and I delta T is I sync tau low, right? And now I have another equation. And if you solve for C1, you get C1 equal to I sync times tau low divided by 2 VDD minus V out minus 2 V diode, right? So equation 3-14 right here is the equation to determine the critical capacitance of value, critical capacitance value of C1, right? Now, if you look at this equation right here, right? Notice that I have the equation for, I believe, the out. Let's see, is that 3-2? Yeah, right here. You see V out equation right there? V out is equal to 2 VDD minus 2 V diode, right? So let's plug in V out into the last equation that we derived, 2 VDD minus 2 V diode. Yeah, from here. What happens if I replace it with 2 VDD minus 2 V diode? What's going to happen with the numerator? It's going to be equal to 0, isn't it? Right? So 2 VDD cancels, right? And then the minus 2 becomes plus. This is going to be plus, right? So this is going to cancel with that. So we have 0 at the denominator, right? So whatever it is divided by 0 gives you infinity. So therefore, this proves the point that for this circuit, output voltage could never be the same as input output voltage. Output voltage could never be equal to twice the input voltage, or in this case, twice input voltage minus the drops, right? Because if you do so, then it would require, if you want this, then it would require very big capacitance C1, right? Any question on this? All right, that's capacitor C1. What about capacitor C2? During tau low, capacitor C2 sources current to the load, right? You might, just like I said earlier, right? While we are charging C1, right? Right here, while we are charging C1 when it's connected to the diode this way, right? This is VDD. At the other end, I am actually, or the circuit is actually supplying power to the load through C2, if there is a load, right? So during tau low, this is low. When C1 is being charged, C2 is now discharging to the load. And therefore, the change in the voltage across delta V across C2 must equal to the change in the voltage across the load, right? So right here. Okay. Now, from the Q equation again, Q is equal to I delta T, which is equal to C delta V, right? Now you can see that I can set them to be equal, C2 delta V C2, right? C2 delta V C2, and I low, right? This is during low, position of the switch. So so the delta T right there should be the T low, right? But the current right here is the current through the load, like as we're looking at C2. So the current that is being supplied by C2 is called I load right there. Make sense? Any question on this? And that's why if I solve for C2 from this equation, I get I load times tau low over delta V out, right? Delta VC is equal to delta V out. So typically we would know what delta V out is, right? That's part of the design parameters. Okay. Any questions? Design example of charge pump. Design a charge pump circuit that has the following specifications. VDD 12 volts, V out 20 volts, I out 0 to 200 milliamps, 1% of output voltage ripple, switching frequency of 50 kilohertz. Assume for the design that I sink is equal to I source, which implies from 37 that tau low is equal to tau high, right? Remember, I sink times I times tau low is equal to I source times tau high, right? So therefore, if I sink, let's just do it this way. Therefore, I sink over I source is equal to, what is it? I tau high over tau low, yes? So if I sink is equal to source, that means what? This is equal to 1, right? This is equal to tau high over tau low. So because of this, I know that tau high must equal to tau low, right? So that's what this means right here. Okay. All right. So again, VDD is 12 volts, V out is 20 volts. So you can see there's a step up, right? From 12 to 20. I out max 200 milliamps. That's I load. Right? That's our I load. Switching frequency is 50 kilohertz. V diode drop is 0.5. Ripple of 1%. Right. So from those given values, I get switching period of 20 microseconds. Tau low is it 50%? Is that what I said? Oh, actually, that's the design guidelines, right? From the beginning, we want tau to be 50% of the duty cycle. So tau low should be the same as tau high. Oh, yeah, that's also from the equation that tau low is equal to tau high. That means it has to be 50%, right? Forget about that. So from here, this implies that there are 50% duty cycle, right? So tau low is equal to the period divided by 2. Tau high is the same thing. So that's going to be 10 microseconds each. I sink from one of the equations is equal to I load. That's our I load times tau low plus tau high divided by tau low, right? Do we have I out max? Yes, we do. We have tau low, we have tau high, and we have tau low as well. So that would give us 0.4 amps for I sink. And once I get I sink, then I can get C1, which is equal to, again, from one of the equations we derived earlier, it's equal to I sink times tau low divided by this whole thing. I get, what is that? At least 1.33 micro. So C1 should be at least 1.33 micro. Keep in mind, this is critical capacitance, okay? Critical capacitance, minimum value. And then C2 from another equation that we derived earlier is equal to I load, which is I out max in this case, tau low over percent ripple that we know. Right? That gives us at least 10 microseconds, microfarad, sorry, 10 microfarad, right? So at least 10 microfarad. So for C1 should be at least 1.33 microfarad. For C2 should be at least 10 microfarad. All right. So I simulated this, looks like, with PSpice. I use 1.55 for C1, and I use 15 micro for C2, right? I believe, if I'm not mistaken, the reason why I came up with these values is because of the voltage, because I need to achieve 20 volts, right? 20 volts from 12. So if, when I first ran the simulation, I didn't quite get 20 volts, and I start changing the capacitance value, and gradually I got the 20 volts right there. Awesome, right? From 12 volts to 20 volts without any inductor. Isn't that cool? So you get a step up converter without inductors, right? And there's the current right there, right? Maximum output current of 200 milliamps as expected. Pretty cool. That's the peak-to-peak ripple on the output voltage. Any questions on this? How do you get, oh, any questions? No. How do you get the efficiency of charge pump? The simplest, less accurate approach will be to use the simple linear regulator approach. V out is equal to VDD minus V diode 1 minus V diode 2, right? Which is approximately equal to minus 2 V diode, right? If they're different, you can just place them differently. I'll put the different values for the voltage across the diodes. But if they're about the same, you can just approximately equal to, just approximate the equation to be equal to VDD minus 2 times a single diode drop, right? And then efficiency would be V out over V in, right? That's actually not a good efficiency, huh? More accurate approach would be use actual measurements of each diode drop. So yeah, so this is approximation, and this is the actual value of the drops. Right? And then again, efficiency would be V out over V in. Any questions on this? If not, that was a step up, right? Can we do a step down? Can we get a step down? The answer is yes. Here's an example of a step down charge pump. Kind of weird to say it because charge pumps means you get higher voltage, huh? But here we have a charge pump that results in a lower voltage, and that lower voltage is adjusted by this R1, by that resistor R1. Right? For unregulated charge pumps, R1 represents the total resistance of the internal switches, which are usually MOSFETs. For regulated charge pumps, the resistor R1 is is a variable resistance that can be implemented by varying the bias of the MOSFET switch in the on state, right? This resistor regulates the charge pump's output voltage, unlike inductive DC to DC converters, in which the output voltage is regulated according to the duty cycle of the switch. Output voltage here is actually regulated by changing the value of this resistance. The switch is controlled by an oscillator that alternates between position 1 and position 2, just like the previous. Oh, I don't know. There's no 1 and 2 here. Should be 1 and 2 there. There you go. Okay. All right, and then I just simulated this. I don't have the design equations for those, but I simulated this just to demonstrate that it is indeed a step down. Input is 12 right there, and then output is right here. And I can get, here's the input voltage, and I can get different output voltages by varying R3. It looks like I get less and less output voltage by increasing resistance.